A very good morning to you all. Hope you all can hear me and have a stable connection to participate with us today. We are about to begin the third guest lecture of the lecture series organized by the Physical Society every year. And even though holding this lecture series online is a little bit inconvenient with the connectivity issues and all, there are some advantages as well, such as we are able to invite guest lecturers from around the globe to connect with us. Because normally with their busy schedules, they might not be able to connect, like come physically to the university, but now they are able to connect with us. So there are some silver linings to holding this lecture series online. And as I mentioned in the previous guest lectures as well, there are a lot for our students to gain here, such as getting extra knowledge and getting to know physics graduates from around the globe working in different fields, and also learning about those fields from someone who is actively involved in that field currently and have first-hand experience. And also the students can ask any and all questions that they have regarding the lecture and the relevant field. This is not something that you can gain from just by reading a book or by reading articles. So this lecture series is actually very important. And mm, also, this lecture, I have no doubt that this lecture will also be a great opportunity for all of us to gain a lot. And without building up any more suspense, I would like to start things off with the agenda. So I give the platform to my colleague Sajana to deliver the welcome speech and start things off. Sajana.
Edihan. Good morning, everyone. It is my pleasure to deliver the welcome speech in the third lecture of the annual guest lecture series organized by the Physical Society of Science Faculty of University of Peradeniya. First of all, I would like to warmly welcome our honorable guest speaker today, Dr. Anusha Liyanage. Then I welcome all the lecturers and all the academic members who are joining with us today. I would also like to warmly welcome all the students of our faculty and from other faculties who are joining with us today. Dr. Anusha Liyanage is an honored past graduate from our faculty, and she is currently working as a medical physicist in the radiation oncology unit of Oroville Hospital, California in USA. Uh, Her talk today will be on nuclear physics, experimental fields, and the path after graduation. I hope today's talk will give an inspiration to all of us, especially to undergraduates like us. Thank you.
Thank you, Sajana. Well, I'm sure our students would like to get to know our guest lecturer a bit before she starts the lecture. So I kindly call upon Dr. Buddhika Dasanayaka to give a small introduction about her. Sir?
Um, I think Rajapaksha just now, Dr. Buddhika phoned me because I think he's having some kind of power problem. Maybe
Oh,
he's
no.
joining. Yeah. So he asked me to do the introduction of Dr. Liyanage. First of all, actually, I really it is an honor to me getting this opportunity to introduce Dr. Anusha Liyanage, who was a student at University of Peradeniya. She graduated with her physics special honors degree in 2004, and then she moved to Hampton University to do her postgraduate studies. And then she obtained her PhD in 2013, doing her research work in experimental nuclear physics at Hampton University, Virginia, USA. She carried out her research work at Thomas Jefferson Laboratory in USA, and after her PhD, she worked as a visiting scientist for a long time at Thomas Jefferson Laboratory. After that, she obtained an assistant professorship at Hampton University, Virginia, USA, from 2018, and then she continued that until 2020. And currently, she's attached to the Department of Radiation Oncology at Oroville Hospital, California, USA, where she is working as a medical physicist. And today she's here with us to share her experience and deliver talk. And so over to you, Anusha.
So good morning, everyone. Is this my time now? I'm sorry.
Did you hear me, Anusha? I'm Varuni here. I'm Dr. Varuni. Did you hear me?
Yeah, I hear.
Heard. Okay, okay. So you may start now.
Yeah. Should I turn on my video? Okay, I will turn on.
Sure.
Hi. Good morning, everyone. And thank you so much, Dr. Senivaratna, for giving such a nice words and like wonderful words. And I have never ever heard like such nice and detailed introduction for myself before. So then thanks again. All right. And thanks. I would like to thank you first of all for the organizers who give me this chance to talk to you all. And also thank you so much for attending this talk, especially because this is Saturday for you. All right. As you already said, Department of Physics, University of Peradeniya is my home institution as well as yours. So I am very glad to be here today. And you already know I am a medical physicist in Cancer Hospital, California. But at this moment, in my mind, I go back to Virginia, Hampton University and Jefferson Lab and become an experimental nuclear physicist once again and talk about some nuclear physics stuff. All right, let me refresh my mind. So I know all of you know what I'm talking about, and let me share my slides. All right, so do you see my slides?
Yes, madam, we can see.
Okay, so do you see my mouse?
Yes, madam, yes.
Okay, great. All right, great. So now you all know what is my title. So I am addressing you, future nuclear physics grads, and I am sincerely apologize for those who already decided not to choose nuclear physics as your graduate studies, but still stick with me and see how fun this field is. All right, so let's go on. So this is my outline. First of all, I'm going to give a little introduction about nuclear physics, and then I'm going to talk about particle detectors. Then I really want to show you how these detectors we used in real experiment. In order to do that, I pull up my thesis experiment. In that way, I can talk a little bit physics as well. And then I want to give you a little heads up on nuclear physics data analysis and simulation. And I will finish my talk with talking about, at the end, I will talk about what to do after graduation as a nuclear physicist. All right. I am talking with my experience and everything. So let's talk what is nuclear physics. Basically, the field of nuclear physics is mainly categorized by energy, low energy, medium energy, and high energy. The very famous Large Hadron Collider in CERN, we know it has the world's highest energy particle accelerator, and that is the biggest machine in the world. Those accelerator can accelerate particle up to tera electron volt, and that belong to high energy physics. So medium energy is about like giga electron volt, and low energy is like kilo electron volt and mega electron volt. Um, in US, we have about 17 nuclear physics labs, national nuclear physics labs, and they all have their own particle accelerators. So in nuclear physics, therefore, we have three main fields of physics: accelerator science, and experimental nuclear physics, and theoretical nuclear physics. So accelerator science is basically work all about the accelerator instrument, accelerator physics. And they do build and test new equipment, but for accelerator. And then they have PhD programs, and especially accelerator science is a multidisciplinary field. Not only physics student can go there for PhD, but also engineering and computer science student also can start PhD there. The experimental nuclear physics, where I am from, and this is what we all the time do. We build and test detectors, and we put the detectors in the scattering experiments, and we collect data and then do data analysis. That's all kind of things we do. So here I put some photographs, and this photograph actually, this is my test setup I used when I work at Hampton University as a postdoc. And this is also, we had a collaboration with the lab in Switzerland. It's the Polarized Target Institute. It's not in CERN, but it's separate, but it's in Switzerland. So I mainly work on that detector. And I used to fly back and forth between US and Switzerland several times per year to work on the detector. And this picture is also at our detector lab at Hampton University, and our graduate students work on the detector. So this is the theoretical nuclear physics, third field of physics. In short and sweet, what they do is postulations and calculations and calculations and calculations. So that is all I can say in short and sweet. However, whatever they calculate, we have to have some agreement with the experimental result. And same for us as experimental nuclear physicists. Whatever the result we obtain from the data analysis, we have to have some agreement with the theoretical prediction. So experimentalists and theorists always have to have agreement between each other. All right, then I'm going to talk about Jefferson Lab. So that is Thomas Jefferson National Accelerator Facility, short term Jefferson Lab. It belongs to medium energy, and the maximum energy we can go for is 12 giga electron volt. And it has an electron accelerator. This picture shows the aerial view of the accelerator site in Jefferson Lab, and this is the accelerator. It is 25 feet below the ground. And this accelerator, we call it, is a racetrack design. So can anyone guess why it called racetrack design? That is because the track horses used to run is exactly the same shape. So that is why our accelerator is called racetrack design. And this design include pair of linear accelerators. All right. Electron accelerate only in this linear accelerator part. Now let's see how Jefferson Lab accelerate electrons. This little piece of model, we call it cavities, and it's made of niobium. So therefore we call it niobium cavities. Inside the cavity is a vacuum, and we have all these cavities all along the linear part of the accelerator, and electron travel inside the cavity. The technology Jefferson Lab used to accelerate electron can be described by only 3 words. That is superconducting radio frequency technology. That's all, and the method to accelerate the electron. Let's talk about that. So we know radio waves are electromagnetic waves, right? These cavities resonate at gigahertz rate. It means, like, we know electron is negative charge and it always attractive to the positive end. When the electron pass inside the cavity and this cavity resonate at high frequency, so electron keep attracting to the positive end and repelling from the negative end. It keeps electron move forward along the linear part of the accelerator, and each step it move forward, it absorb energy from the electromagnetic radiation. Okay, that's all about radio frequency technology. So how the superconducting part come? Jefferson Lab is the only lab used superconducting technology to accelerate particles. So it means everything need to be ultra low temperature. Everything need to be ultra cold. This is the linear part of the accelerator. This is the inside the tunnel, and this is the linear part of the accelerator. And this big, we have this big pipe and our cavities inside here. However, the electron beam is even thinner than human hair, all right? But still, our beam pipe is this big because we have cavities inside and then we have liquid helium circulating all over the cavities all along the linear part of the accelerator. So we have all liquid helium inlets and outlets and all the pressure control systems and everything. That makes this beamline this big, right? That is the accelerator part. And then now we accelerate electron all along this linear part, and then we have to bend all these electrons. That is the fixed structure of the accelerator. So we have to bend all the electrons, no matter what energy they have, all the electrons have to bend on the same radius of curvature because that's the fixed structure. So how do we bend those with different energies? This is how Jefferson Lab reached that goal. This picture shows at the bending end of the accelerator, and each blue box here represents dipole magnet. We have 5 dipole magnets vertically aligned, and each dipole magnet has different magnetic field strength. So all electrons come here and they have accelerated and they come to the end of the linear part of the accelerator, and they separate according to their energy so that each electron can select right magnetic field so that in order to bend the same radius of curvature as other energetic electrons. It means all, no matter what energy, they all have to bend same radius of curvature. It is done by doing having dipole magnets with different magnetic field strength. Once they all bend, and all the electrons come back to the same beamline and accelerate once again, and then bend it once again. So once electron complete one full orbit, electron acquire about 2.2 giga electron volt. And that means when electron complete 5 full orbits, it reach its maximum energy. All right. So that's all the accelerator part. And this is the mission control room. When accelerator is turned on, when accelerator works, so all accelerator scientists and engineers has to be here 24/7, and there are so many parameters to watch just to make sure accelerator work perfect. So once we have accelerated electrons, Jefferson Lab has 4 basic experimental halls, A, B, C, and D. These experimental halls are all also built underground, and the size of these inside the experimental halls are like few storage building. So like if you can see, there is an average height person, average size person standing here. Obviously he's taller than me, and compared to his size, you can get some idea how big inside the experimental hall, and then the size of the detectors nearby. And this is also some other experimental halls. All right, that's all about the accelerator and experimental halls. Now I am going to talk about particle detectors, as I promised in the first slide. So when we talk about particles, it can be charged particle or neutral particle. So for charged particle, it can be electron, muon, pion, kaon, proton, anything. So uncharged particle, we can have neutron or photon. So these are, no matter what particle is, these are invisible particle, right? So we cannot see those. However, we have methods to detect those particles. Let's say we can detect the time when particles pass through certain location, or we can detect a position in 3D space when this particle pass through some location, or else we can determine the energy of the particle, or else we can determine the type of the particle, whether it is electron or proton or pion or kaon or what kind of particle. However, this is what to detect, but how do we detect the particle? We cannot see it, right? So this is how we detect particle. Let's say when charged particles pass through a material, the atomic electrons in the material absorb the electromagnetic energy coming from that moving particle, and that electrons get excited and de-excite by emitting photons. These emitted photons we call scintillation light, and this is the main theory behind all the particle detectors. This is the only thing we can detect, no matter what detector. This is the only thing we can detect. Even in CT scanners, X-ray detectors you see in your hospitals, they use the same method. No matter what, to detect invisible particle, this is the only key point. Okay, now let's see how we use that method to build detectors. First of all, I'm going to talk about scintillation detectors. That is, we use for particle tracking and timing. Scintillation is a special kind of plastic, and it has two main characteristics. First one, it gives the fastest timing. So therefore, any experiment we do, we always use scintillation detectors to get the timing because it has very fast response time. Let's see how detector work, how this scintillator get into work. Let's say when charged particle pass through this scintillator like this, an atomic electron in that scintillator get excite and de-excite and emit photon. The second characteristic of the scintillation material is they do fully internal reflection. The emitted photon doesn't go out. We don't lose those photons. Instead, the emitted photon do fully internal reflection like this, and we can collect those photons at both ends of the scintillator bar. So in order to do that, we connect PMT. It's a photomultiplier tube. It's a little piece of instrument. It's so expensive. What it does is it absorbs all these photons coming toward it, and then it converts to the PMT convert these photons to electrons and amplify, so that at the end we can see electric signal. So let's say that is how scintillator work. Let's see how we use it on experiments. All right. So this is really scintillator detector we used in experiment. What we do is we stack scintillator bars on top of each other from bottom to top and create a scintillation wall. This is exactly what it is. However, each scintillator bar, both ends, we have two PMTs connected, right? And when charged particles pass through this wall, PMT, we can get the signals from the PMTs. And if all these scintillators are horizontally placed on top of each other, we can get the Y coordinate where the particle pass. And only one coordinate is not enough, of course. So then what we do is same detector plane, we make 90-degree angle so that we can get the X coordinate. It is exactly this one. Let's say one detector plane gives us X coordinate, and the second detector gives us the Y coordinate. It gives both X and Y particle position in 3D space. However, if we want to make a track, one coordinate is not enough. We use the same two detector planes at certain distance and imagine here. So we get the second coordinate so that we can make a track. And also, as I mentioned before, scintillator gives the fastest time. So we can detect when the charged particle pass through these scintillators, and then we get the time, and then we get the time here, and then from this time difference, and because we know the distance between these scintillator planes, I can get the velocity of the particle. All right, that's all the scintillation detector. Now, second detector, I am talking about the drift chamber. It is also used for particle tracking. So this is a cross section of the drift chamber, and it's very big in size. Always these detectors in nuclear physics is like a big area, like walls. Okay, this is a cross section of the drift chamber, and then it's about like 10 centimeter thick. And inside the drift chamber, we have field wires and sense wires alternatively all throughout the detector, and they are spaced between like 0.5 cm between each other. So we give very high negative voltage to these top and bottom layers and the field wires. It's about like negative 2500 volt, and our sense wire is at ground potential. It means inside the detector, we have very high electric field. So this detector is filled with mixture of gas, argon and ethane, 50-50 in percentage. What happens when particle pass through this detector? So when charged particle pass through the detector, it ionizes the gas inside the detector, and all the negative charge particles attractive toward the sense wire through the electric field lines, and we get the signal on the sense wire. So how do we use this to build detectors? How do we use this method to build on our experiment? Here it is. As I mentioned before, scintillator always gives the fastest time. So we place scintillator plane, scintillator detectors on top of our drift chamber just to get the time when the charged particle pass through it. And then the same particle pass through our drift chamber, and accordingly we get a signal in the sense wire. From this drift time, I can determine how far charged particle pass through from this sense wire. All right. However, like for the scintillator detectors, we use X and Y coordinates only. For drift chambers, most of the time, we always use 6 coordinates, 6 planes. We call X, X prime, V, V prime, and U, U prime. Like same detector planes, but we place it in angle between like about 45 degrees between each other and make 6 coordinates. And at certain distance, we place the same 6 planes and get the second 6 coordinates so that we can make a track. The track, if you remember, we used scintillator detectors also to make track. However, the track we get from the drift chamber is more precise than scintillator detectors. All right, that's the tracking detectors. The third detector I am going to talk about, gas Cherenkov detector. We use it to identify particle, just to make sure whether what particle it is, whether it is electron or pion or kaon, what particle it is. This is how we do that. When charged particles pass through a material, and when, if it is faster than the speed of light in that material, it emits Cherenkov radiation. However, because the particle is faster than the light, the emitted Cherenkov light looks like a cone, uh, like emitting backward. So it's like cone. It looks like a cone backward. And always this angle theta is the constant for specific particle. This cosine theta is defined by 1 over n times beta. N is the refractive index of the material, and beta is the velocity ratio of the charged particle to the speed of light in that material. All right. So let's see, how do we use this to identify a particle? Let's say I want to identify electrons. For electrons, I can determine the theta. For electrons, I can determine the theta, right? And I place mirror at that theta angle so that all the Cherenkov radiation reflect backward. I just want to reflect all the Cherenkov radiation backward so that somewhere behind I can place a PMT which absorb all this radiation and convert to electric signal. All right, so this is what we do at experiment. This is what I explain. So let's imagine again, if I want to identify low mass particle, let's say for electron, I know the theta angle, and then I place the mirrors and reflect all the Cherenkov radiation backward so that I can detect, I can see the electric signal using this PMT. And same time, if I want to detect, identify high mass particles like proton, I know the theta angle to place the mirrors for the proton, and I do the same thing. I absorb all the photons coming from all the photons and convert it to electric signal. That is gas Cherenkov detector we always use to identify particles. The fourth detector is a shower counter or calorimeter to determine the energy of the particle. That is basically made of lead glass crystals. So it is really looks like it's really ordinary glass, but we have lead in it. Lead is a very special material element so that it can absorb all kind of particle energy. So usually lead is very useful even in medical physics field. We always use lead for as a shield because it absorbs all the radiation energy. It has the ability to absorb all the radiation energy. So we have here, this is a real detector we used in our experiment, and it is a lead glass array. We create array of lead glass crystals, and cross-section area of one crystal is about like 10 by 10 centimeters square, and this crystal is about 10 centimeter long, and PMTs attached to each crystal. Each crystal is taking care of, they have their own PMTs. All right. So what happens is when charged particle pass through this lead glass array, all the way it pass, it charged particle lose energy. All this energy is absorbed by the lead in the crystal, and we have PMT attached to that crystal, which convert to electric signal. However, if we want to determine the total energy for the particle, we add all the PMT signals together and we get the total energy. All right. This is the basic 4 detectors we always use any experiment, not even in any experiment actually, even LHC. They have the same theory. They have the detectors with the same theory behind it, but the shape of the detector and the size of the detector, they all depend on the experiment, all right? But theory is the same. So now I really wanted to show you how these detectors I just discussed use in real experiment. But before I go to that, in order to do that, I chose my thesis experiment so that I can talk a little bit physics as well. So that is actually the title of my thesis experiment, my PhD thesis experiment. The title is Proton Form Factor Ratio, GE over GM from double spin asymmetry. Right now, don't worry about the title. I am going to explain everything. The name of my experiment is Spin Asymmetries of the Nucleon experiment. In nuclear physics, you will never find short-named experiment or short-named detectors. They always have very long names and nobody can memorize it. Therefore, we always used to use acronyms. So therefore, my experiment is same. If I go to a conference and if I say I'm talking about spin asymmetries of the Nucleon experiment, only very few people will understand what I'm going to talk about. But if I say I'm talking about experiment say, then everybody will realize what I'm going to talk about. Okay. All right. So now let's see what are the form factors. I am going to explain what is my thesis title. That is the physics behind all the physics behind it. So form factors. We know electron is point-like particle, right? Nothing inside the electron. However, proton or nucleons is proton and neutrons are nucleons. And inside the nucleus, we know we have gluons and quarks inside. So they are not point-like particle. So form factor describe how the nucleus deviate from the point-like particle. All right. And also we know that proton and neutron, they have internal structure. They are quarks and gluons. The form factor describe the internal structure of the nucleon. Let's say as an example, let's say for proton, we have quarks and gluons inside, and proton is like a ball, like a little sphere, right? And we all know it has a positive one charge. Nobody can point a single space in the proton and say that positive one charge is localized to that space. No one said that. No one can say that. The positive one charge is distributed all over the proton. That distribution is described by electric form factor, GE. Here, electric form factor GE. It describes the charge distribution all over the proton. Similarly, we know the proton has spin 1/2, and therefore it has a magnetic moment. And that magnetic moment distribution is described by magnetic form factor, GM. Okay, that's all about the form factor. However, we can measure these form factors from elastic electron proton scattering. And we know that in particle physics and nuclear physics, we are not talking about classical mechanics. We are talking about quantum mechanics. All these both form factors are function of form momentum transfer. Let's see here. We have proton here. Okay, we have nucleon, and then these three lines represent three quarks. And when an electron comes here and then scattered by an angle theta, it transfers form momentum to the proton. That transfer form momentum we can calculate if we know the incoming electron beam energy and outgoing electron beam energy and then scattering angle. We can measure them through the experiment, and we can determine this form momentum transfer. And both GE and GM are function of this form momentum transfer. All right. Again, GE, that is the charge distribution of the proton. It's a function, distribution function. If I integrate that distribution function all over the proton at q squared 0, it gives positive one charge. That is what we know. That's what we know, right? Positive proton is positive one charge. And similarly, if we integrate our magnetic moment distribution all over the proton, it gives us the magnetic moment of the proton. That is positive 2.79. All right. All right. Then I'm going to talk about proton radius, how it relates to the form factor. As I mentioned before, we can determine the form factors through scattering experiment. And they are also function of Q squared. These are the real experiment data. I can measure electric form factor as a function of Q squared. And if I interpolate my data to Q squared 0, and the slope gives the proton radius, we can determine the proton radius from the slope of this graph at Q squared 0. However, we cannot measure anything at Q squared 0. Instead, what we can do is we can measure here even as an example, let's say we can measure electric form factor at the lowest Q squared we can reach through experiment, and then we interpolate the data to the Q squared 0. However, this method, we really need accurate knowledge of electric form factor at low Q squared to determine the proton radius, to determine accurately the proton radius. All right. This is a very important thing, and like we have so many experiments to determine the proton radius. There are so many lot of experiment world around has done to determine the proton radius, and all of them has given some proton radius value within some their error band range, so that we all have agreement to have one proton radius. However, in 2013, we had a different experiment method. It gave completely different proton radius. It's about 8 sigma difference from the previous value. And since they published it, there are so many experiments still going on everywhere in the world. And this method, this technique always gives the same. They reproduce the same result. But now it's being like 2 radius for the proton. However, proton is just a proton. It can have only 1 radius. It should not matter how method we determine, right? So this has been a big issue in nuclear physics community, and it's called proton radius puzzle. Yes, of course, it's a puzzle. So proton is the most fundamental particle we all know, but can you imagine that we still don't know what the size of the proton? We know only the charge of the proton. So one of the possible reasons to have this discrepancy can be uncertainty of determining electric form factor at low Q squared. Remember the last slide we talked about? That can be one possible reason. But then, why do we care about it at all? Okay, now only, maybe you know now only, or we don't know the radius of the proton since 2013. Until 2013, we knew only one value. From 2013, we have 2 values, and then everybody puzzled. We don't know what is the radius exactly. And then, okay, why do we care about it? It did not change our lives, and we still alive, and then we still keep doing whatever we used to do, and then it did not affect our lives at all. So why do we care about it then? This is why proton radius relate to Rydberg constant, and why Rydberg constant is important. Those who are doing atomic physics, they should know Rydberg constant is a fundamental constant, and it relates to the all other fundamental constant like electron charge, electron mass, Planck constant, speed of light. They all are related to each other. how about proton radius is different than what we think? Then my Rydberg constant, our Rydberg constant will be different, and all these other fundamental constant will be different. And we know all these constant to high precise, right? We know up to several decimal places. If the proton radius change, and if the Rydberg constant change, and if all these constant change, it will not change in big scale. It will change only the decimal places, but it changed. All right. That's all about proton radius. However, so one possible reason to have that is the uncertainty of determining electric form factor at log Q squared. So electric form factor is more accurately accessible through the form factor ratio GE over GM. And there are so many experiments well around doing to still doing to have the measurement for GE over GM. It is also a function of Q squared. And these are the data we have. So basically, there are three main methods to determine GE over GM ratio. First method, the data come from first method shows these black data points, and those are looks like a GE over GM ratio is flat. It does like, it looks like it goes straight line, is flat. However, the colored data points are from the first, whatever, the first experimental method, first method, black data points we obtain. That method is well established and very, very popular, and everybody do that. And it's it's been using for like several decades. The second experiment method, these colored data points are from the second method, and it is not old as the first method, but this one is using more than a decade. And you see how difference we see between these two methods. GE over GM ratio is just one value at per Q squared. But now we have two different experimental method gives two different results. When we go high Q squared values, we even see bigger difference. It's dramatic discrepancy between these two methods. And we have several theoretical predictions, and only as I mentioned in the first few slides, only theoretical predictions not work. So we have to see experimental evidence, and there are so many experimental experiments going on to solve this. Well, so we start to talk about GE over GM ratio to get the precise GE, to get the precise proton radius. However, now we are facing another problem. All right. So now the third technique to measure GE over GM ratio, we call double spin asymmetry. And this is the experiment we focused on through my thesis. All right. That method nobody has used before. Only one data point, only one experiment used that method to determine the GE over GM ratio, and it is this green data point. It's at log Q squared, and it's just one. Nobody used this method because there are so many practical and technical difficulties utilizing this method. However, our experiment saying we targeted to use this method to determine GE over GM ratio at these two high Q squared values. Okay, now I guess now you have better understanding of what my thesis title, determining the form factor ratio GE over GM from double spin asymmetry. That's my thesis title. All right, so this is my goal, to determine GE over GM ratio. All right, so our experiment ran in Halsey Jefferson lab, and this is inside the lab. And here our accelerated electron beam comes, and then this is our target. And then we have two main detectors. First one we called beta detector, and then second one we called HMS detector. Let's look in detail. Beta detector, big electron telescope array. Okay, So here comes the basic detectors I talked at the beginning. Here it comes. So we have our target here. Our target is here around somewhere. And then we have a whole bunch of scattered particles. And then we have forward tracker. It is just planes of scintillator detectors. And just right next to the target to track. And then we have a Cherenkov detector to identify what kind of particle it is, whether electron or proton or what it is. And then we have hodoscope. Hodoscope is just a common name to address the scintillation detectors. And at the end, we have calorimeter for the energy, to determine the energy. All right. So when we build detectors, we can put our own names. That's fine. So the second detector, high momentum spectrometer, that's HMS. Again, this is the scattered particle come from this side, and then we have two drift chambers for particle tracking, and each drift chamber has 6 planes on it. And then we have hodoscopes, again, 2 planes of hodoscope. Each plane has 2 hodoscopes. Each hodoscope has 2 planes of scintillator, gives X and Y coordinate. If you remember, each scintillator has 2 PMTs attached to both ends, and then you see this side, these are the PMTs on this side. And this is the first plane, and then after some distance, we have the second plane here, and someone is working on it. And then we have, that's for the particle tracking and timing. And then we have gas Cherenkov, again, to determine what kind of particle it is. And at the end, we have lead glass calorimeter at the very end of the detector step. However, can anyone guess why we have the, okay, let me ask this way. Can anyone guess what happened if we place a detector behind the calorimeter? Will you see a signal or not? What do you think? You will not see any signal because the calorimeter, when charged particle pass through the calorimeter, the charged particle dump all its energy to the calorimeter. So nothing left afterward. If you place any detector behind the calorimeter, you will detect nothing. So therefore, always any experiment, we place the calorimeter at the very end. All right. Okay, so now I'm going to talk about polarized target. This is the biggest issue we have using this third method, double spin asymmetry. That is why people did not use this, because there are so many technical difficulties and practical difficulties used to polarize the target. First of all, my target is to determine G over GM ratio for proton. So I need proton. As a proton target, we use crystallized ammonia. Okay, this is the crystallized ammonia here you see. And this is called target ladder. And we filled crystallized ammonia in aluminum target cups. We basically have 2 target cups just to fill aluminum, and these target cups made of aluminum, and it's about 2 centimeter in diameter. And this carbon and CH2 targets just for the calibration purposes and background purposes and everything else. So, however, in this method, we need to polarize the target. We use dynamic nuclear polarization technique to polarize the target. That technique needs 1 Kelvin temperature and 5 Tesla magnetic field. Here we come to 1 Kelvin temperature, again like in accelerator, linear accelerator part, right? So ultra low temperature. How do we reach it? So this is our target ladder, and then we immerse our target ladder inside the liquid helium bath. So it always in 1 Kelvin temperature. So, however, we need to provide 5 Tesla magnetic field to polarize the target. How do we do that? We use pair of superconducting coils. Like we place this pair of superconducting coils one is left and one is right, like laterally, so that and they are superconducting. We immerse those coils are also in liquid helium bath, and it provides 5 Tesla magnetic field across the target. So it is so hard to control the liquid helium at 1 Kelvin temperature. If the temperature goes a little bit rise, so then it's complication happen. So then it's so hard to control it. That's why people did not use this method. All right, now I am going to talk a little bit about analysis. And when any scattering experiment happen, there are tremendous of charged particles scattering all over. We don't need all those. Let's say that even my experiment, I needed just electron and proton, just like I needed electron and protons scattered from hydrogen. That's it. Everything else is garbage. We don't need it. All right. So, but we spend most of our time at graduate college for data analysis because of this invisible particle. We have like bucket of particles, and we have to dig for the right particle to find right particles what we need. So coincidence experiment play a big role in this level. Let's say incoming electron beam here, and then it's scattered from the target, and we detect that electron in this detector. Same time, uh, we detect recoil proton in this detector. What the coincidence means, we need to detect electron at exact time when the proton is detected on the other detector. If I detect electron little later time, I don't want it. I put it on garbage, right? So this is like a little example of it. This red center you see, they are the electrons we detected right at exact time when the proton detected on the other detector. They are the really coincidence in it. However, we put little timing window, and that in green region, they are the electron detected little later time okay. But all around this blue is like electron detected little longer time. After a little longer time, we don't need it. It can be from any scattering. We don't need it. So having coincidence experiment is very, very important to subtract the background. That's really helpful. All right, here I just want to show you how we use Cherenkov data. Remember Cherenkov detector? We place mirrors to identify what kind of particle. So at the end, we have bucket of charged particles, and we need to identify only electrons from all of them. How do we do that? Remember, we have Cherenkov data. These are the Cherenkov data we have, and see, for the data we have big electron peak showing because we put mirrors to at that specific theta angle to determine electrons only. So that's why we have big electron peak, and some pions and some photons somehow get through those. So then I see little peaks, but still they are very negligible. And then I can apply Cherenkov cut to get to remove those unnecessary peaks. These are a little bit about detectors again. Nothing works 100% efficiency. Same for the detectors. Detectors are not working for 100% efficiency. We have to determine the efficiency, the acquired data during the experiment, and then we have to correct for the efficiency. Both a drift chamber and Cherenkov, and even a calorimeter and scintillator detectors. We need to do that for every detector. All right, this is the simulation. So here on all plots, yellow is the simulation and blue stars are data. So simulation play a very big role, especially in nuclear physics, because we don't know what is happening really right at time when scattering happens. So even before, as a graduate student, even before real experiment starts, we spend lot of time to build up the simulation. It includes everything in the beamline. We have to include everything in all the materials, what electron sees when electron travel, and then we have to include all the detector detailed materials, and then we have to include all our target materials, everything exactly like in real experiment, so that we can compare our simulation with the data. So in this plot, we see our simulation match very well with the data. So we are very confident that we understand it's not some mysterious thing. It did not happen any mysterious thing during the scatter, right? That make us confidence. And if we see like this, our data and simulation is not match each other very well. So we really understand that there is something wrong, and it can be because it is about our data analysis. We have to find what it caused and we have to correct it before we further moving into. Okay, the simulation is very good to understand if something mysterious happen at the target at the scattering. The simulation again, especially this experiment, simulation play a big role. We wanted to have proton scatter from hydrogen. We wanted to have proton and scatter from hydrogen, right? So then, however, electron recoil proton from every materials it sees on its path. So in our case, we have proton coming from liquid helium, and then we have proton coming from aluminum, and we have proton coming from nitrogen, and we have proton coming from hydrogen. Our detectors detect all the charged particles pass through. The detectors does not know how to distinguish what contribution of proton come from what target material. We have to find a way to distinguish determine the different target material contribution. So this is the simulation I did to simulate the proton contribution come from different target material. Here different colors shows the different target, like light blue shows that's the proton contribution come from aluminum, our target cup. And here red is the proton contribution come from helium because everything is immersed in a liquid helium bath. And then green is the proton contribution come from nitrogen because we use NH3 as a proton target. So these all are background protons. However, if I add all the target contributions together, it perfectly match with the blue stars. That blue stars are the proton contribution we detect from our detectors. As I mentioned before, detector detect all the proton. No, it does not care where that come from, right? So once I have my simulation perfectly match my total target contributions match perfectly with the data, then I am confident that I understand each target contribution and I can subtract my simulated background, which is proton contribution come from nitrogen, helium, and aluminum from real data to extract the proton come from hydrogen. All right, that's the struggle we like. I spent a lot of time for this simulation to extract real proton. All right. So let's say, even though, okay, all I talk about, like it took only 10-15 minutes. However, it took years for real analysis. All right. So somehow, okay, I have final result and I obtain my systematic and statistical error estimations and I defend my thesis and I publish my result and I am done. All right. So now I want to talk a little bit about my result here. So this is the 2Q squared. This is the GEO-GM ratio determined from our experiment in blue. but nobody want to spend millions of dollars to have a measurement with this error bar, this big error bar, right? So, however, anything can happen during the experiment. Unfortunately, during our experiment, very unfortunate situation happened and it lost about 1/3 of data collection time. So we did not have enough statistics. So therefore, my error bar is very large. However, we can say one thing. So our data, so this is our first method and all our colored data point. Do you remember? All our colored data point come from the second method and they all about here. And we from our method is close to the second method to determine GE over GM ratio. We expect it. From theoretically, we expect it. And we found that because this method, nobody has done it because it's so hard about handling uh, polarized target. However, we learn how to handle the polarized target during this experiment. So this experiment opened to the world that, okay, we can do this experiment successfully. And unfortunately, for our situation, we had something wrong at the target, but we can do successfully this experiment. Then initially, we wanted to redo the measurement, we wanted to, because we already know how to handle the polarized target, we wanted to um, do the experiment again. And initially we thought to do, and then somehow I changed the field, so somebody else will do it. All right, so now I think this cartoon is so perfect for us. And first of all, when we get offer from graduate college, we really get happy, right? We impressed, we really like happy. So then how about oppress and depress? It's no longer valid. I don't agree with it. That's why I put cross mark on it, because our advisors are so good, so helpful, so kindful, and I really disagree with this too. However, this one I really agree with this one, because basically for nuclear physics graduate students, average graduation period is about 6 hours, 6 years. So about first 2 years, 2.5 years, what we do is we build and test detectors, and we need to take some classes for graduate level classes, and also we need to build a simulation. We are busy. However, so the experiment runs about 2-3 months. Like it depends on the experiment actually. Some experiment runs years, and our experiment did run 3 months. It depends on the experiment. Rest of all our time at graduate college, we spend time for data analysis. How do we do this data analysis? This is, we are looking for some invisible particle out of like sea of other garbage particles, right? So we have, it is just computer programming, computer programming, computer programming. So that's why then I like this part of this cartoon, because it's mostly pressed. We do computer programming. Rest of like 5-6 years of our graduate student life. That's what we do. However, now let's say I finish my data analysis and I present my result in front of the committee, PhD committee, and then uh, I uh, I defended. That's called defending the thesis, and then I publish my result, and I'm done. Right? Do you think I really done? Let's think about it. So when we go to school, we have teachers to guide you, right? And then you go to university, then you have professors to guide you. And then you go to graduate college, we have advisors to guide you. But but afterward, when we graduated, when we get graduate, there are nobody to guide us. We have to find our own way. And that is the really story begins. And that welcomes to the real world. All right. First thing come to our mind, job. That's the very first thing, the most important job. And what kind of job we want to, what kind of job I can do as an experimental nuclear physicist, and how to find it, where to find it. It's like so many questions, right? And let's think what you really did at graduate college. So you did a PhD and now you are doctor someone. And if you did experimental nuclear physics, then you are an experimental nuclear physicist. What you did at graduate college, all is fundamental research. That is very hard of the matter. You did research on neutron, proton, or like any other charged particle, anything or gluons or quarks, or it's about the nucleus. That is very hard of the matter, and that is fundamental research. And you discover something through some research, and it will someday unlock the secret of the universe. It will help to understand the Big Bang theory and everything, but they are fundamental research. So being an experimental nuclear physicist, first of all, before I talk about jobs, I really like to talk about the immigration status. When you get an offer to come to States for the graduate college, you get F1 visa. You get F1 visa. That is student visa. You cannot work here. You can only go to the school and graduate college. You can study. After you graduate, from your PhD, we have special 2 years. We can work, and that special 2 year we call OPT, optional practical training. And but still we in F1 visa. Still we are in student visa, but we can work these 2 years. However, after that 2 year ends, if you still decide to stay in this country, then you have to find an employer who offer H1B. H1B is the working visa. So not all the employers offer H1B. You have to find an employer who offer H1B. And then later you can decide whether you get green card and citizenship, everything later. All right. So now let's talk about jobs. It's very important. Whatever you find the job, that is the job you will be working all rest of your life, right? So it means that you have to like it. Okay, first talk about academic job. If you really like to do academic jobs, doing postdoc is really help. Like in your graduate college, you focus on only your thesis experiment. However, when you do postdoc, it means like when you work as a postdoctoral research associate, short term is postdoc, you have several projects to work on. So different project has different physics. So you exposed to a big field of nuclear physics and you get a lot of research experience. So that postdoc period is very helpful if you want to find an academic job, because when you go to academic, then you continue the same. You do research and you can write, you apply for grants and get money to run experiments, and then you plan experiment and you can choose any labs to run those. You can get a PhD student, all kind of things your professors doing. And also you can teach. Excuse me. So these all academic jobs. All right. So let's say if you want to find non-academic jobs, and there are so many options out there for non-academic jobs. However, I put these three jobs in red due to a special reason. This is different. As an experimental nuclear physicist, there are so many defense-related jobs. They are very good research and development jobs. And you all know NASA, right? So research and development projects, lot of. And then even nuclear power plants, they have research and development projects, and they all are so interesting salary scale and then very comfortable jobs. However, As an alien nuclear physicist, we cannot go for those jobs. I say early alien because we are not born in US. So only US citizens can do these jobs because these jobs need high security clearance. And we don't have that. Only US citizens can have high security clearance. Or else like at least we need to have permanent resident to do some of these jobs. So right after I graduate, I just apply for some NASA jobs for fun, and then they really like. I had 2 interviews, and they really like my simulation work, but uh, my immigration status was I was in OPT, so story end of story. So I was in OPT. However, um, there are, but these three are just only one option. There are so many options out there. Like there are so many data science. It's very popular nowadays. Data science jobs. Big companies like Google, Facebook, Apple, or any big companies, they really like nuclear physicists because we have an experience of handling big data sets and simulations, and they really like to hire nuclear physicists. And you can find a data science job easily, and also they offer uh, working visa, and you will never find a job to do the same thing you did at your graduate college, right? You never find same workspace. So then wherever job you do, wherever go for a job, even data science, they train you first, 6 months or a year, they train you first and then work on. And you can go to medical advancement like I did. However, you need to spend 1 or 2 more years of studying medical physics. And also you have engineering projects, Wall Street jobs. There are so many jobs because when you get graduate, all right, you have PhD, but it's not the only one you have. You come out from the graduate college as a full package. It's about like you have done so many years of data analysis. You have a lot of experience of programming, and you have big experience of simulation, and you have you are good at critical thinking, problem solving. You come with complete package. So and you can manage, you can handle any job. And I just want to say that like you don't have to be panicked to choosing nuclear physics. Nobody gets lost after graduate from nuclear physics. Everyone find a job, but finding a job is harder, right? Even in Sri Lanka it's harder, but we find a job. um, and before I finish my talk, I really want to encourage you, if you plan to come to US, get a graduate college in nuclear physics, it's really important if you have if you get any experience of programming, because most of the time we spend at graduate college, we do data analysis, that is programming, and we mostly do C++, Java, Python. If you get chance to study, or if you get chance to like experience or acquire some additional skills about programming, it will make your life so easy here. When I come first time, I have no experience of the programming, but I survived. And even it's not a must, but your life will be more easier, much easier. You don't have to do computer programming, computer science in the university. When I come to Peradeniya. University of Peradeniya. My first year, my combination was chemistry, physics, and computer science. But later, I a little bit regret about choosing computer science instead of choosing maths, because chemistry, physics, and maths, I have to come to the university to learn. However, for computer science, I can learn it from outside. There are thousands of courses, computer programming, whatever we want to learn. There are so many courses outside. So if you get chance to do any of these and get some additional skills about computer programming, that makes perfect. Um, All right, and yeah, all right. This is end of my talk, and then in this world, nothing is impossible nowadays. And if I can do all these things, you can do. And I'm really thank you all for staying with me, especially because this is Saturday for you. And again, I thank you for the organizers. I really appreciate and I sincerely thank for organizers for inviting me for to talk to you all and share my experience and everything. Okay, now you can ask any question. Even you can ask me any question, even Sinhalese. That's fine. And you can ask me any questions or any comments. Very welcome. And also you can ask me questions not on nuclear physics. You can ask me any question on medical physics. Um, I did not have time to talk about medical physics, but if you ask any questions regarding the medical physics, I will try to give you the best answer. So, all right, your time. Thank you so much for listening or not sleeping, at least.
Thank you, madam. Thank you so much. I know everyone will agree that the lecture was very informative and it was presented in a way so that all of us could understand, even people without a good nuclear background. So thank you very much. So as madam said, now let's move on to a small Q&A session where students can ask any and all questions that they have regarding the lecture or the relevant subject matter. And also, if you can't ask them out loud, please drop a message in the chat box, or if there's some connectivity issue or something. So I'm sure madam will be happy to answer them for you. So I encourage all students to take use of the opportunity and ask. But first, our lecturers might have a few questions. So after that, the students can follow. Thank you.
Yeah, Anusha, I hope you can hear me. This is Yuguman.
Yeah.
Okay. It was a marathon presentation. I mean, it's more deeper and more informative. And thanks for the last few slides that you dedicated for our students to kind of talk about your after graduating part. And I really appreciate that you already mentioned that computer science can be done outside the curriculum here we have. That is not many people get it because you just spend time on computer science just rather than you study the physics or maybe chemistry or maths. Anyway, one thing I want to kind of want you to do, because I asked my second year students to attend to these lectures because they are in my medical physics program or in the course. So I don't want them to get disappointed. So just tell them, how do you get to the medical physics from the nuclear physics part? Or how easy it is to somebody to join directly to the medical physics program. All these accreditations and, is it really tough, or what are the preparation they have to do? Thank you.
Oh, yeah, of course. I really love to talk about it. So basically, medical physics, field of medical physics is very competitive here nowadays. Like when I come to graduate college, I had a choice whether go to nuclear physics or medical physics. So because I didn't know any of them by that time, I chose to nuclear physics path. But if like in medical physics, it's really strict for accreditation. And if you apply for medical physics uh, degree, medical physics PhD here, you really need to find whether that university is accredited or not, because accreditation is very important for the medical physics field. And like not like nuclear physics field, we have very limited opening for PhD in medical physics field, because like nuclear physics field, they have millions of grants and one professor can get several PhD student, but medical physics basically like one student, one university get one student, like it's very competitive get to PhD. But once to get to PhD, you still you can have like normal PhD path like 4 5 years to get graduate. And it's really important, really important whether before you apply, of course you can get the position, of course you have the ability and you can get the PhD offer. You first of all, you really need to find out whether that university is accredited or not. Otherwise, even you get PhD, still you have to follow other extra courses because it's not accredited. It's another headache. So you really need to, first thing to check is whether it is accredited or not. And once you get here, it's normal PhD. But then, like let's say the way uh, I did my PhD in nuclear physics, and then later I, because I don't have any, if you, even if you come to directly to the medical physics degree, or I am from nuclear to medical physics, always they have set of courses to follow. It's very accredited courses, and I have to take those courses from accredited university. Otherwise, it's not helpful. So I did all those courses in accredited university. You have to do the same thing if you done any other PhD. And so all these courses are same courses as a medical physics master student and medical physics PhD student, and we have same curriculum, same courses. In the class, we stay all together. It's the same curriculum. However, any science PhD is not only physics, chemistry, or computer science, or any STEM field PhD can move to medical physics. How do? We have to take these courses from accredited university, and it's exactly like master degree in medical physics. However, the difference between master degree and our degree is master degree student and we take the same curriculum courses, same courses, but master degree students have they have to do little simple research for the second year. But we already have PhD. We have 5-6 years of experience of research. So therefore, we don't have to do research anymore. We just need to complete the courses, all the courses required, and then I can get into medical physics. But in the medical physics field, then we have uh, certification and moving forward. But that's how we get into medical physics. Any not only physics, as I mentioned before, any PhD, computer science or biology, especially. I guess I don't know, biology people maybe for biology student maybe it's easier because I was having very hard time to study about anatomy and biology because I did maths for A level, and this is the first time ever I started studying biology and anatomy, and I really appreciate the superpower of memorizing things biology students have, because it's so hard to memorize all these words, but somehow I get through. But all these set of courses, there are set of courses in medical physics. These courses same for whoever moving from PhD to medical physics or medical physics master degree or medical physics PhD degree, same set of courses. So, and did I answer you all?
Yeah, that's fine. Yeah, we'll wait for the students. I mean, if they have any particular question, you can answer to them. That's fine.
Okay.
Yeah, thanks. Yeah, thank you very much. Yes.
Welcome.
If there's no other, I mean, there will be other questions, Anusha, but until then, I would like to ask, like, briefly tell us, like, the difference, like, between Fermilab, Jefferson, CERN, like the major differences for us to know, because we are not from this field. And
yeah, I barely hear you, but you asked the major differences between Fermilab, Jefferson Lab, and CERN and all this, right?
yeah, different
The most important major difference is the energy, the accelerator. They all have their own accelerators. the energy they reach, like let's say Jefferson Lab, the maximum energy we can go for giga electron volt, and Fermi Lab goes for even about higher than that, about 200 giga electron volt, I guess. And then LHC is the biggest energetic accelerator. So then it goes to tera electron volt. What happened when the energy increase? Like let's imagine like we have an electron and we want to smash the nucleus. So it means electron need to go to inside the nucleus, right? So it needs higher energy. It means like when the accelerator has the higher energy, the physics we can study is different. Like LHC, they smash the nucleus. They talk about quarks and gluons and discover new particles because they have superpower. Like they have highest energy, and then they have even not they have not electron. They have even proton accelerator. So all kind of physics is different with the energy the accelerator can provide. And also this basically LHC is a proton antiproton collider. It has two accelerators. It can collide proton and antiproton together, and then it's a different, completely complicated physics, completely different physics. In Jefferson Lab, we have only electron accelerator and we have medium energy, and we can smash the nucleus, but not like LHC. Fermi Lab is higher energy. It has a higher energy than Jefferson Lab. Basically, Jefferson Lab is 12 giga electron volt maximum, and Fermi Lab goes like 200 or over 200 giga electron volt. Not as much as LHC fan, but each different energy means different kind of physics we can. Did I answer for you?
Yeah, thank you, Anusha. Thank you. And there are some questions in the chat box.
Oh, chat box. Right. Oh, yeah. Okay. Okay, one asks, can a medical physicist who graduated from CAMPAP, non-accredited university from Asia, join residence medical physics program in US? Okay, so the question, Buan, I'm sorry if I pronounce your name wrong. So someone asked, can the medical physicist who graduated from CAMPAP, non-accredited, like university, it's like if someone graduated from non-accredited university from Asia, join the resident medical physics program in US? No. So the short answer is no. It's because always the medical is always very strict about this accreditation, because in order to accredit, if a facility want to get accredited, it has to fulfill certain criteria about education level and about the safety, and then lot of criteria to fulfill. So therefore, if I get graduated from non-accredited university, I cannot go residency. And again, for everyone, if I go to medical physics, if now I did not go to residency yet, I have to later. But when I became a medical physicist in future, I had to do residency like a real medical doctor. But our residency is like only 2 years, and we learn all about medical physics with that 2 years, all the radiation therapy techniques and all technique and everything. So that residency, get into the residency is also very competitive here. And if you are graduated from non-accredited university, no, you can't go to residency. So you have to then take some courses here from accredited university and become eligible to apply for residency. Otherwise, you are not even eligible to apply. So, and then someone asked, I guess I answered for that question. And then someone asked, what is the reason for accelerated cavity to be made out of niobium? Okay, that's a really good question. So niobium has a special, like, okay, the cavity, inside the cavity is a vacuum, and the cavity resonate at high frequency, and then we want to accelerate electron. We use niobium, it's a special kind of material still with superconducting level. When it goes to superconducting, uh, ultra low temperature, then niobium behaves like it's it has a specific characteristic which give the perfect uh, it gives the perfect environment to accelerate the electron. It's a always we use niobium. Someone asked, what are the protective measures taken in the experimental labs against high energy radiation? All right. First of all our accelerators, not only Jefferson Lab, most of the labs, accelerator and experimental halls built underground. That is for radiation safety. Because when any scattering happens, so many charged particle and high radiation goes everywhere. We cannot control, and so many particles. So we try to expose those radiation to the human or animal by building everything underground, so that at least we can minimize. But because we are sure that no person underground or no animal nearby, and also uh, even though they built underground, the walls of the experimental hall and even in the tunnel, walls and roof and the floor, they are like 2-3 feet thick concrete, and it's like very impossible to pass through all this thick concrete. So then we are safe. It's a very it's like that is a security, like a people safety issue, and that's very confidence that everyone is safe, and that's why they built underground and they put thick buildings, thick walls, and everything safe. Then someone asked, oh, okay, someone asked, I have heard that quantum black holes are made in a large hadron collider. If so, how are they useful to us? Well, let me think about it. So I really, nothing come to my mind at right away now. Quantum holes, are they useful to us? I don't know. I'm sorry. Well, I remember this question, and of course, I will find the answer, and I promise that I will contact your professor and give the answer, so then you can, Budin, right? I don't remember if I spell wrong. I'm sorry. So yeah, I will find the answer and give you through your professor. All right. Then is Cherenkov radiation harmful? So any radiation is harmful anyway. So it is radiation. Even when radiation goes to human body or animal body, so it destroy even our DNA, right? So any radiation is harmful. It depends on the energy of the radiation. However, Cherenkov radiation in our labs, they are harmful. Yes, but nobody exposed to that radiation. When experiment runs, nobody can get into the experiment hall. It's completely fully sealed. We can just open the door. We have to follow security steps. and not a single person going. There are so many rules and so many safety procedures. So, so that even when an experiment, after experiment complete, because there are so much radiation inside, and because of this radiation, the material get radioactive, right? So materials nearby get radioactive. So after experiment complete, even people cannot go into the hall until we have a special group. They are survey group. They come with a special equipment and then check the radiation level. And until the radiation level goes down, nobody can enter. And then even we cannot bring any instrument from inside to outside because most of them are radioactive. So we cannot bring them right away. It's like so many procedures to follow. So yes, Cherenkov radiation is harmful. Okay, then someone asked, what is the present situation? Oh, it went up. Let me find it again. Oh, okay. What is the present situation in this nuclear field and medical physics with all of these about grants, chances? Oh, yeah. Okay, so regarding, so okay, all this nuclear physics field is run with grants, right? So basically in US, all national labs funded by Department of Energy or National Science Foundation, and they give all the grants from them. So far, there are sometimes like with economics, and then sometimes we get sometimes we get some travel ban, and it's like different political ideas and political powers. They all can change. At sometimes they stop funding, but due to pandemic they don't stop. So then still everything work fine, and then even the pandemic situation, student working and do research, and everything happen online now, but it's not big deal right now, specifically because of the pandemic, no. But sometimes time to time different political issues and all kind of things can come. Who knows, can those things can happen. But for pandemic it is not. Even medical physics is not, because medical physics, anyway, we have very less opportunities for the medical physics, lot of opportunities for the nuclear physics, because a lot of grants, lot of money spent for nuclear physics research, but not specifically for pandemic. Oh yeah, someone asked, can we use radioactive substances in scintillation detector? Yes, that is what exactly we do for testing the detector. When we build any detector, especially scintillation detectors, we need to test, right? So how do we test these detectors? We cannot have really electron beam to test our detectors, because to produce accelerated electron beam, it takes thousands of dollars per minute. So they don't give electron beam just to test the detectors. How do we test these detectors is, first, we have free cosmic radiation. That is for free. So we test with cosmic rays, but it's very low. We get like, if you put a scintillation detector outside, or even in your office or in the lab, we get like one cosmic ray per 2 minutes. It's very, very rare. So in that way, we cannot acquire like 1,000, 2,000, 10,000 events at all. So in that case, we use radioactive material, because radioactive material gives the radiation in high rate. It depends on what kind of material, even like sodium, or if you have cesium radioactive material, it is a high energetic, right? So it gives a high rate of radiation. And then if you can use sodium or low rate radioactive materials, but that's how we test the detectors. Okay, so someone asked, can you please give a brief explanation about the operation of the PMT? Oh, that's great. All right, PMT, photomultiplier tube, right? PMT is the photomultiplier tube. It is like a little tube, and when we send when we direct photons toward the photomultiplier tube, we have the first thing photon phase is a cathode. It has a metal cathode inside this PMT. We have a cathode which which absorb this photon energy and emit electron. Remember what that called? It's a photoelectric effect, right? It absorbs the photon and then emit electron. That is the photoelectric effect. That happens at the cathode, which is at the very front of the PMT. PMT is just like a tube. And very front, we have a cathode, and we have a photon hit on the cathode, and it emits electron. After this cathode, we have little piece of metal, we call it diodes. And it's like diode is placed like a zigzag. How to say it? It's like, it looks like a zigzag. And this electron emitted by cathode, so between this diode, we have very high electric field. And once electron get emitted from the cathode, it meet first diode, and within that period, it gets some more energetic because we have very high electric field between them. Electron get more energetic so that it amplify the number of electron. It means like each time it hit the diode, each time it amplifies the number of electrons so that at the end we see big, like it amplifies like 10 to the power 5. Like if I get 1 electron at the end we get like 10 to the power 5 electrons. It's like it amplifies electrons so big amount, and we see really big signal, electric signal at the end. That is how PMT works. The diode is the issue. Diode is the key point inside the PMT because they accelerate electron, they make electron more energetic, and if electron have more energetic, so then it has more power to produce more electron. That's right. I guess I answered that question. And someone asked, what is the quality of life of medical physicists in USA? What is the quality of life of medical physicists in USA? That is very interesting question. Let me think about my life. That's very cool. Okay, as a medical physicist, okay, first of all, we really work on something, we cannot make mistake, right? So because we are dealing with human life. So if we like earlier time, people have done some mistake, and then patient died right on the spot when treatment happening. But nowadays we have several steps. If I basically I do treatment plan for the radiation therapy for the patients, and if I do some mistake on my treatment plan, if nobody else catch the mistake, I deliver that plan to the patient, and patient can be died on the spot, and then that is the end of my career. However, that is not right now. We have whatever the plan I make, doctor check it, definitely. Doctor has to approve it. So if I do some mistake, doctor return the plan back to me. However, but we are not supposed to make mistake. And quality of life is the medical physicist basically supposed to do. We have treatment therapy machines, and physicists. We are the physicists. So the treatment machines, we deliver the radiation. We need to have it high precision. So we have several procedures to test the machine, like we have to do every morning before treatment starts, or and set of tests for every month, and very complicated set of tests for annually. And we have set of tests we always have to go through just to make sure machine works perfect and millimeter precision level. So, and the quality, again, that's a first job we need to do, and then we need to do treatment planning. And it's really interesting, and it's really responsible. It's a responsibility, big responsibility. When I learned the medical physics classes at university, so then what they tell us that for teacher, we can, if we make some if I solve a problem in the blackboard, if I do mistake, I can erase it and then redo it. But for medical physics, I am not supposed to make that kind of mistake because I am dealing with human life. So it's like a bit responsible, but it's not big stress because work environment is so good, and everyone is so nice for me right now so far. But who knows? But so far, what I can say is there, and even in medical physics field, I am just getting to medical physics. But when I with time, I have to do fully certified. I have to become fully certified, and when I become fully certified, then it's very comfortable life, and then very interesting salary scale, and good. But even now, it's very it's, I would say it's very good field, and I would say it's all up to your choice. I had very good time in experimental nuclear physics, and but then I was doing all fundamental research. And that's why I changed to medical physics, because I really wanted to see real application, like fundamental physics. Even let's say proton radius, who cares? I mean it's important for the science community, but I don't see any application. That is the main reason I moved to medical physics. I had to work so hard to move to medical physics because I did all these studies doing work at Hampton University. But I move here because whatever I do now, I see real application. Let's say I make a treatment plan and then patient get complete all the treatment and walk away from the facility happy. I feel happy about like I help him to live few more days like that, at least few more days. So then that kind of happiness comes, and that's what I really feel about medical physics. That's why I moved to medical physics. So then it's about quality of life in medical physics. I really think it's really good and happy, like all other subjects, but we have to be really very responsible sometimes. And yes, it's any job, yeah. It's not only medical physics. Whatever job you go, you have some responsibilities, you have some task to complete. That's normal. But because we are dealing with some human, not not a detector, not a this is real human. So then we have to be fully responsible. But otherwise, it's really good. Someone is asking.
Madam,
Yeah.
sorry for interrupting. Actually, the time allocated for our event is actually running out. So any other questions that they have, I think they can email you or
Oh,
see.
yeah. So I have only two questions left at the end. I'm so sorry. So can you
Okay.
please
Okay,
email
madam.
those
Yeah,
questions?
yeah. I'm
It
pretty
said,
sure they will.
it said Dihan Sena did ask
Yeah.
me one question, and oh, you can see that.
Yes. Yeah.
Oh, okay.
Okay. So
All right.
we'll
Yeah.
email you the questions that we have. Some others have questions as well, so they'll email you
Yeah,
and
yeah,
get
sure,
back to you
sure.
to us because the time
Ask
is
me.
running out. So thank you so much, madam, for your insight and answering all our questions. It was invaluable. So as what they say about all good things, our events also have to be wrapped up and it's kind of at the end. So to properly thank everyone who helped make this event a success, I would like to call upon my colleague Danuka to give the vote of thanks. Thank you, madam.
You're welcome and stay safe, everyone.
Yes.
So, Diha, can you hear me, dear?
Yeah, we can hear
Can
you.
you
We can hear you. Yes.
hear me? It gives me an immense pleasure to deliver the vote of thanks for giving to all the dignitaries assembled here. First
I
and foremost,
barely hear. I'm sorry. I barely hear
Yeah.
you. Danuka.
Like if you can close up on your microphone or something, because the sound like we can't hear you properly. It's like it's very faintish.
You mean me?
No, no, no. The
Oh, okay.
Danuka like
Diha, now
Um,
okay?
now it's fine. Now it's better.
Thank you. First and
Okay.
foremost, my heartfelt thanks to our guest, Dr. Anusha Liyanage, a medical physicist and radiation oncology at Oroville Hospital of California in USA, who, despite of her busy schedule, has found time to raise this occasion about nuclear physics guards. Truly, it was a very lovely lecture and interesting subject. So, thank you very much, madam, for your thought-provoking and interesting address. Next, I would like to thank our newly appointed department head of physics, Dr. Sivakumara, for the guidance he gave in organizing this event. I must mention our deep sense of appreciation for Dr. Varni Senaviratna, former physics department head and senior lecturer, for the support she gave coordinating this event and introducing our guests to us. Then I would like to thank to the Senior Treasurer of Physical Society, Senior Lecturer, Dr. P.W.S.K. Bandaranaike, for his presence and cooperation for this event. Further, we are grateful to all the lecturers of our physics department and to the demonstrators for their guidance and support. Last but not the least, I thank my colleagues, members of Physical Society of University of Peradeniya, and especially for fourth year brothers and sisters for their fullest cooperation in organizing this event a resounding success. So finally, I would like to acknowledge our gratitude to all the participants who participate to this valuable webinar from every corner of the world. Thank you. Yeah.
Yes. Thank you, Danuka. Well, we have reached the end of our event, and also please note that the recording of this lecture will be uploaded in the YouTube channel of the Physical Society of Peradeniya. And make sure to pass on this message. So if you benefited something, the others can as well. Well, I think it's time to wrap it up. So wish you all a very pleasant day, and thank you so much, madam. Again, thank you so very much. Thank you all. Thank you.
welcome, everyone. Stay safe. Bye bye.
You too, madam.